I'm continuing. So we are employing Nemo guardrails. These Nemo guardrails, in a sense, like can act in two ways. It can alter the response. It can safeguard the response. So the altering the responses based on the predefined rules. It guards the output responses, making it blind friendly is the role for the Nemo guardrails. And how do we do it? We do it in this way. So we ensure the responses are in compliance with the predefined rules that we have set to it. And the implementation is done in the following ways, where you have a config file that you're going to define your LLM provider. So in the experiments, like in the implementation, we did use NVIDIA AI endpoints, and we have set general instructions for them, and we have configured the Rails, and we have certain sample responses conversations in this config file. And actions.py is something that you can write a piece of code in Python stating that these terms are really offensive, and if you see that if the response contains these terms, please do not reply anything. So such kind of configuration is being done in actions.py, and all the things like the configurations and actions are being defined in this rails.co. So both the things get defined in this rails.co. This defines the guardrails flow. We are setting the flow of the guardrails accordingly. So this is how the Nemo guardrail is being implemented in the project. This will help in altering the responses and making it blind friendly. Okay, now let's discuss about the flow, how it really does it in terms of architecture way. So the first module we are going to discuss is the input management, where you have a person who is blind wearing smart glasses. So there are two things that you can obtain from him. One is that the person is going to speak to the system, the audio input and the image input. So these two things are the ones that you're going to get from the person. And since we are dealing with the system to develop a system that is like personalized, where I only can use it but not by others, so we need a user identification. We did use voice based authentication. Based on the voice, the system recognizes the user, and if the user is recognized, it then sent into a speech to text module, where the speech that the person is speaking gets converted into text. And here the Fusion Hub maintains the synchronization of inputs. Here we have the text input and we have the image input. Both are maintained at the same time. That's the role of Fusion Hub. And this is the path of input. Now we have two inputs ready. One is the text and one is the image. So two inputs we are having in ready. And let's stick to this point, and let's skip to this point where where we did use latency management, which I was talking in previous slides, that our system has a latency management, which means that based on the response time taken by the multimodal LLMs, the execution flow of the flow is altered. For example, we may not be sure that MLLMs would give a response in a specific time. The major disadvantage of even when you use ChatGPT, it's going to take a lots of time to think anything or to respond you back. So in such cases, if the latency is so high, then we can implement this image to text model plus a simple text-based LLM rather than a complex MLLM. So with this workflow, we could reduce the inference time or response time. If the latency is like normal, well, good enough, then MLLM is preferred, and we can just ignore this image to text module. So this is like our solution also contains execution path optimization based on the latency management. So the other module in the architecture is the cognition engine. This cognition engine is the core of the whole model, where the all AI stuff is gonna be inside that. So we have this latency management, which I have just briefly explained, where based on the response time of the AI, the flow gets varied. So the latency management chooses the image to text model. If the latency is really high, so this dotted arrow indicates that it's an optional workflow, need not always be executed. Only when the latency is low, you're gonna execute you're gonna use this flow. Yes, and next is behavior-friendly prompt instruction, which will, as we know, for LLMs, we do need prompts to be given. So defining the role of the LLM is something that is the one that we're gonna give over here. And the next is reasoning engine. Engine indicates that you're gonna use text-based LLM and multimodal LLM. Text-based LLM in terms of your optional workflow when your latency needs to be managed, and multimodal LLM, which takes the input from the prompt that the user is giving, and the image. Here the red arrow indicates the image format, so and the image that you're sending. And the next is the BVR-friendly response maker, which the output from the reasoning engine need not always be, as I mentioned, the output of any reasoning engine or the LLM, if we do not set it properly, need not always be BVI friendly. So to make it a more friendlier responses to for the blind, we're gonna use Nemo guardrails. As we have discussed in the previous slides, we have set predefined rules, and we have set in the actions.py. So that is being implemented over this BVF friendly response maker, and you're gonna get the output.
So if you don't mind, let me add a couple of points here so that it's more clear for the audience. So basically for the reasoning engine here, we are using a multimodal LLM, right? So that uses image plus the text. However, we observed, and I wish you were mentioning that, we observed that MLLM is considerably slower than LLM, right? So therefore, when we are in shortage of time in terms of latency of getting back to the user, because we want the system be real time, right? We don't want like give back answer to the user like in 1 minute. We want it to be in few seconds. So basically, what we have done here is making that reasoning engine adaptive based on the latency between LLM or multimodal LLM, like a single model LLM, multimodal LLM. And then when we have like a single model LLM, that latency management, we recognize that, and we convert that received image to text. So they're basically identifying objects within that and add it to the prompt so that we at least have some clues about what is going on in that picture. Right? So, yeah, and then we make it to the reasoning engine.
So can I have a question? So, I kind of assume that latency may come from like network communication, which as kind of assume that user can be anywhere, and network may be not reliable, and it may take longer to do it for MLM.
Here we don't have assumptions about network. Here is more like the MLLM versus LLM. So if you run these two, we notice that the MLLM is the slower.
In the edge device, if you could say, you are maybe thinking about the network, right? Let's assume it's in the edge device. The MLM is giving you lots of time in terms of latency.
So everything is on edge.
So which mean that like who gonna decide the target latency, like user or like
the latency? We assume that like in a conversation, there are some certain latency that to make it like a natural conversation.
Okay, so which mean that from my understanding, like if you use the same MLM and within like constant environment, like let's say age, the like execution time should be roughly the same. I guess I'm not sure. I mean,
because first of all, to run it because it's like more billion parameters obviously than a simple one. To load the model in a cold start condition, it's gonna restart the model and it's gonna run it, right? So that's where it's gonna take a lots of time.
But after you like load the model,
that's in a warm start.
It consistently same time.
Yeah, but in cold start you can consider it is like taking a lots of than a simple LM, right?
Okay. Let's assume that it is a warm start and it's consistent, right? So if you meet that state, it means that you have the same kind of latency for the MLM. And then you don't need to switching between them.
I think that maybe the reason would be if your hardware is like currently being
low battery,
battery or there's lots of processes already happening and you need something lighter.
Yes, that makes sense.
Since an edge device.
So yeah, and I think somebody doing it.
Yeah.
Oh yeah, someone I think added to the
yeah, I hope. Okay. So after this cognition engine, let's now place together all the pieces that we have discussed. So we have three things majorly: the input management, which makes sure that the inputs are ready, the text input and the image input is being ready. So that is being sent to your next module called cognition engine, where that is sent to the latency management, and whole the process remains same as we have discussed previously. And that red, if you could see over here, this red arrow indicates the image, and that is being sent from this image input actually. So that is the part of cognition engine, and you get a response which is behavior friendly, and this response is sent to your next component, which is response management, where you have text to speech. And that's how your response management, cognition engine, and input management work together to make the system ready. And this is the architecture for my first contribution, which includes for the BVI individuals. But whereas my second contribution is about BVI users in public spaces. So if you could see, you are in a museum. There you could see there persons are in a museum. They're wearing smart glasses, and they would be going to the art pieces, and asking about like what exactly is the piece of artifact about. Such kind of in these kind of scenarios, you need not need the necessity for user identification, because everyone would be using the smart glasses, and need not necessary that the smart glass is always personalized to the user, because the same smart glass can be used by other person, and so on. It can be shared. Basically, in a shared environment of the product, you don't need a user identification tool, but rather you would be needing age determiner and safe query filter. We are incorporating the age determination factor, which means that based on the voice of the person, you're going to decide the age of the person, and the response are altered accordingly. So for kids, you would be requiring to filter out some kind of responses. For adults, you would be needing to filter out or alter some kind of responses. So we incorporate the age determiner for that, and we utilize the CNN and LSTM for the age determination. And why exactly we need the safe query filter? So we did use Llama Guard. As we are dealing with the edge devices, we did use 1 million parameter, which because it is like simply to deploy in the edge devices. So this safe query filter makes sure that the privacy, since we are talking about a shared environment, these kind of questions can be filtered before sending it to the main reasoning engine. So the unsafe questions can be unanswered prior sending it to the cognition engine, whatever. So we are placing this safe query filter that is dealing with the Llama Guard that has this 13 different hazardous categories being categorized as unsafe. So all these hazardous categories is being filtered as unsafe, and so prior sending to the cognition engine, that was the one that I was mentioning. So prior sending it to it, we use this age determination and safe query filter, and we filter most of the queries if it is unsafe. So the adapter architecture for this Audo-Sight public remains same. Most of the architecture remains same as to prior one, but in replacement of user authentication, we would be doing the age determiner and safe query filter over here. The rest of the architecture would be same as we have seen in the previous slides, in the architecture of that, in the BVI individuals. So this is the second contribution. Let's come to the implementation details. We do agree that we have proposed the solution, we have proposed an architecture, but we implemented the following components in our experiments, where we did speech to text, safe query filter, multimodal LLM, and BVI friendly response maker and text to speech with the respective configurations. So it's like the speech to text is given to the multimodal LLM, and this is going to give a text-based output, and that is sent to this text to speech. This is the implementation details. Whereas in the architecture, we have proposed a broader view of our achievement, like what we intend to achieve in the end. So in the experimental setup, So for the reasoning engine, as we have multimodal LLM, we did try about two multimodal LLMs. One is with the lava and one is in the cloud. We did observe that the lava is going to take a lots of time to get the output. Like it is taking around like 20 to 15 seconds in here to run in the edge device and get an output. So which is why for the reasoning engine, for the experiments, we have used a Hive model endpoint for the experiments in the reasoning engine. That Hive model endpoint is the Meta Llama Vision Instruct with 11 billion parameters. And the edge device that we did use is the MacBook with 8 GB RAM. And the data set is like Viz VAQ, this is visual question answering. So to run the experiments, we have chosen this data set because this data set is the one which was taken by the blind people. So it originates from natural questioning answering setting with the blind people, each took an image and recorded spoken question about it. So this data set was taken by the blind, and it is like related to the project that we are talking to, which is why we have chosen this. I think just a minute. Oh, so yeah, and when it comes to the evaluation, so here is the result for the evaluation of cognition engine, where we have tried to give a different query length to the cognition engine, one with the short, one with the medium, and one with the long queries being asked. We got to know that the query length does not affect the latency of cognition engine. Rather, the weightage of words affect. So it's not about how short your query is, like how medium your query is, like, but rather than what kind of words that you are really asking to the system. That's where the latency is being calculated, and you could see that there is some outliers over here, which we are trying to resolve in the further future works, where if the response time is too high, we're going to reduce it using the latency management in our future works. And this is the impact of Nemo guardrails. These are the blind-friendly response or unsafe categories that we saw in the prior sites. And with the Nemo guardrails, there are nearly the percentage of inappropriate responses are decreased with the usage of Nemo guardrails is the whole goal of the experiment that we could see. And this is the implementation of cognition engine alone, cognition engine, or else like if you could say combination of the input to the response manager combinedly, but in a Gradio. Gradio is something that we used for web development. I could just play a short demo over here. When I ask a question, so it is saying it's white, like. So the whole goal of the experiment is like without Nemo guardrails, it is telling the color of the like whatever the object is, even though I did not ask it, which is actually not needed for the blind persons. So with Nemo guardrails, such kind of things can be avoided. Oops. So there is no such responses like white ball or whatever it is. You intend to get the major things like the cucumbers are present, such things. So this is the short demo for the implementation of cognition engine. And the last contribution is the integration of the Audo-Sight that we are discussing and with the smart sight. So here you could see a smart glasses, which has the camera over the front, and you could see a Raspberry Pi Zero over here. Image gets captured over this, and the captured images is being sent to the edge device like laptop using the SFA protocol. And in the laptop, we would be having a script for you for now we are using YOLO and facial recognition models. So based on that, you're gonna get the response, and you're gonna convert whatever the YOLO detection object is gonna object detection facial recognition, and is being set back to the audio. Like text to speech is also being performed. This is a smart site prototype which we have in live as well. I could show the demo in the end. So integrating active and passive perception. So we need to, the goal of the thesis is like to provide an ambient perception for the BVI. There are two ways to integrate this. Like the ambient perception can be said as like an active perception, where it can be dealt with talking to the system, giving instructions, or talking to like talking actually to the system. But passive is something that you don't need to trigger the system, but rather the model would be responding you back. So that is where the passive is going to be like the object detection or facial recognition. So as for BVI, both the things are actually needed. So you fuse the both to get a proper guidance. So in the third contribution, we're actually integrating the active and passive perception. So here is the experiments, experience and expected outcomes that I intend to provide. So we have attended the sports extravaganza, which is like the event for the blind and visually impaired, encouraging them in sports activities. And this is the demo that we gave in the Lions Club. Me along with the professor and along with my co-teammate Jacob. So it's about demonstrating the reaching out to the wide audience that our product is being developed, and showcasing them, and helping the blind can be said. So with the help of the products, making them understand why prototypes need to be designed, and we basically showcase our product in this event. And my next expected outcome would be targeting to the HPCC conference, where I have like there would be a submission on 30th April for this conference, and so I would be planning for my next expected outcome for this. And conclusion can be said as like the whole thesis conclusion is like combining the vision and audio for real world assistance, enhancing safer responses, and avoid inappropriate words. Like you can say it as like a blind friendly response is our conclusion, and making the system accessible for BVI individuals in both at homes and in public, and demonstrating the workflow using the web-based as we have seen in the Gradio. The future works can be said as all the works that we have, like till now, the experiments are ran in edge devices majorly. So we are planning to implement the workflow over the edge to cloud. And the second future work can be said as detecting the mood of the person based on his voice. Like you can say adding the emotions to the LLM responses. For example, if the person is so scary, his question or his tone would be different. So based on the tone of the person, their mood can be detected, and emotions like the responses can be altered accordingly. And evaluating the multimodal responses based on evaluation criteria, like increasing our number of experiments, and evaluating the LLMs or fine tuning them would be the next like future works we could say. And we could show a short demo.
So, this will be showcasing both.
So this was the prototype that So this was the prototype that I was discussing.
Yeah, so first I'll showcase the passive perception so that it can just see what's going on in the environment here.
So passive perception here indicates the YOLO and facial recognition, where I'm not interrupting the system, but it is gonna tell what objects are being recognized.
Yeah, so you can see whenever I've got like an orange here on the table, which I don't know if you can see that very well, but yeah. So if I put these on.
Mouse, laptop, drink, orange,
Orange.
You could see objects are being detected.
apple,
And then, yeah.
orange, person, drink.
Saw my hand, thought it was a person. And so, and then it can also do facial recognition. So
Yeah,
yeah.
Person, clock. Dr. Amini is your professor from the University of North Texas.
So the thing is, we have trained the facial recognition for Dr.
Laptop.
Amini alone. So for now, it's going to detect Dr. Amini.
Yeah.
Only him.
Yeah, right now it's all turned on. And
I
then,
hope it's audible. I don't know what the people
yeah,
are hearing.
hopefully you can hear all that. And then, yeah, I've got turned up. All over.
Okay.
Oh, that's my sister texting me.
Oh. Bad ways.
Disable that, okay. So yeah, and then here's the active mode. So if whenever I start talking to it, I can ask it to describe it right here. So, it'll take a moment to respond because it's.
Yeah, it's gonna run the alarm.
Yeah. Please, oh, wait, hang on. Actually, I was covering it up because I wanted to, make sure that it's not just saying what all the objects are whenever I started that. So give it one moment here. Sorry about that. I'll just go ahead and restart it here.